Hi folks, this is section 4.4 and this is from the notes, a couple problems that I had skipped, so I want to go back and show them to you. It's page 15 of your notes, and we're going to do problem 5 and problem 7. Those are the two that were skipped before. And these are pretty long, especially number 5, so you may want to start on a different sheet of paper. I think I'm going to end up using another sheet of paper myself. We're looking for concave up and concave down in any inflection points, and that's information from the second derivative. So we need the second derivative, and that will require the quotient rule to get there. So we have f prime of x for the first derivative is equal to low x squared minus 4 d high 2x minus high x squared plus 3 d low 2x all over low x squared minus 4 quantity squared. And we are going to simplify this before taking the derivative again to get to the second derivative. And so we can distribute from the back. And when we distribute this 2x, remember there's a negative in front of it, so you can distribute negative 2x instead. This will be then 2x cubed minus 8x minus 2x cubed minus 6x all over the denominator. And then we can combine like terms. That 2x cubes are opposites, which is wonderful, and they're gone. And so we have f prime of x is equal to negative 14x over x squared minus 4 quantity squared. And from there we'll get the second derivative. So f double prime of x is equal to low d high minus high d low, the quotient rule again. So that's x squared minus 4 squared low d high minus 14 low d high minus high negative 14x d low, bring the exponent forward, 2, rewrite the base x squared minus 4, take 1 off the exponent so it's first power, times the derivative of the base, which is 2x. All over low, so now our x squared minus 4 is to the fourth power in the denominator. And here we have two terms. Here's a term, and here's a term. And we want to take out the greatest common factor. And in each of these, it has a binomial factor of x squared minus 4. So we're going to factor that out, because then it will cancel with the denominator. And we take out the lowest power. So this one's to the first power, this one's to the second power. We'll take the one out to the first power. So when you're doing that, recall if you take out x squared minus 4 and you're not sure what you get, you can multiply by the x squared minus 4 like you're used to doing on the outside. And on the inside of your parentheses, you rewrite the original thing that you're factoring. I'll make this into a plus. And I certainly could have cleaned up a lot of that on my way. Oh, no, I made a mistake. You're dividing each of these by the same thing that you're multiplying by on the outside. So there's x squared minus 4 here for this term. And then we have, pretend this isn't here. I wish I could erase, but I can't. And then we're also dividing this second term by x squared minus 4. And close my parentheses, and then here's the whole denominator, which is x squared minus 4 to the fourth power. So again, I wish I could erase this, but this isn't, this fraction bar is just here, and then it stops, and then there's a new fraction bar. So this is going to give me, well, let's see, the x squared minus 4 is here and here, they cancel. So now this will be to the third power, and I don't have to write that other one. So my denominator is x squared minus 4 cubed. And my numerator, when I reduce these, I'm going to have x squared minus 4 to the 1 power, you subtract the exponents. So these reduce, and then there's still this negative 14. And now we'll go over to the other term. We have a plus, and here the x squared minus 4's cancel altogether. So we're left with the 14x times 2 times 2x, which is, let's see, 56. Yeah, 56x squared. And now let's keep simplifying by distributing. This is still the second derivative. F double prime of x is equal to negative 14x squared plus 56 plus 56x squared over our x squared minus 4 cubed. And I'm going to use a different sheet of paper here to continue. And so when we combine like terms here, squared terms, we have f double prime of x is equal to 42x squared plus 56 over the denominator, x squared minus 4 cubed. Okay, so we want to find out where the second derivative is 0, where the second derivative does not exist. And so you're going to set the numerator equal to 0, and you're going to set the denominator equal to 0. Moving up. So when we set the numerator equal to 0, we have 42x squared plus 56 equals 0, and we subtract 56 from both sides. So now we have 42x squared equals negative 56. Divide by 42 on both sides. And your next step is to take the square root. And here's where you run into problems, because you can square root the left side, but you cannot take the square root of the right side because it's a negative. So when we set the numerator equal to 0, there's no solution. So we are not going to get any inflection points from there. When we set the denominator equal to 0, you can cube root both sides, and that gives you x squared minus 4 equals 0. And you can factor the difference of two squares, x plus 2 times x minus 2 equals 0. And we get x equals negative 2 and x equals 2 as our possible inflection points. But wait a minute here. Let's go back to the original. It can't be an inflection point for the function if it's not a point in the function. And notice with our function, if we plug in 2 or negative 2, it zeroes out the denominator. These are not inflection points at all. They're asymptotes. But the beautiful thing about this is that we haven't wasted any steps. We still do the same thing. We're still going to make our interval. We're still going to break it at negative 2 and 2. And we're going to check concavity on all three parts of this. Negative infinity and negative 2, negative 2 to 2, and 2 to infinity, because concavity can also change at asymptotes, just like increasing and decreasing can also change at asymptotes. So negative 3, 0, and 3 are my test points. They are going into the second derivative. So I'm plugging in right there. The second derivative evaluated at negative 3, and I really only care if it's positive or negative, so I know the concavity. Let me move up a little bit. If I plug negative 3 in the numerator, it's going to be squared, so it becomes positive times a positive plus a positive. So the numerator is going to be a positive something. If I plug negative 3 in the denominator, this will become 9 minus 4 is 5, and cubed is something positive. So if I have a positive divided by a positive, I know that the whole thing is going to be positive. So I'm going to put a plus above there to remind myself. And now for 0, the second derivative evaluated at 0 is equal to, and here we can see this term zeroes out. We would have 56, which is positive. And in the denominator, you would have negative 4 cubed, which is negative. So this will be less than 0, negative. And for testing 3, the second derivative evaluated at 3, the numerator will be positive. The denominator, 9 minus 4, 3 squared minus 4, and then cubed is going to be positive. So that one is positive. In the second derivative, positive interval means that it's concave up. It opens upward. It holds water. In negative 1 means concave down. It opens downward, would not hold water. And then concave up again. And again, this is information of how the function that the second derivative came from is behaving. So we have our interval, let's see, concave up, if we officially write this, is from negative infinity to negative 2, union 2 to infinity. Concave down is negative 2 to 2. And then we can't say, if these were part of the domain, we would call them inflection points. But because they're not part of the domain, they can't be an inflection point if they're not such a point. So there's no IP, no inflection points. Okay, so that takes care of number 5. Let's move on then to number 7. Yes, 7. And for this one, I just want you to get some practice with ease. So again, I'll start in your notes, and then I'm going to move over to paper because there's probably not going to be enough room. The first thing I'll do maybe I'll just use some of this room up because you already have those notes. So I'm going to rewrite it first. As f of x equals 1/2 times e to the x minus e to the negative x. So I just want that 1/2 going along for the ride. I don't want to deal with it too much. And now my f prime of x is equal to 1/2 going along for the ride, and I can take the derivative term by term, moving over. The derivative of e to the x is e to the x, minus the derivative e to the negative x is e to the negative x. But I need the derivative of the exponent. Here the derivative of the exponent was 1. Here the derivative of the exponent is negative 1. So instead of having minus e to the negative x, when I multiply by negative 1, we'll be adding instead. So that's my first derivative. And now the second derivative, f double prime of x, is equal to 1/2 going along for the ride. The derivative of the first term, e to the x. And remember, the derivative of the exponent's 1, so we don't need to write it. And then the derivative of the second term is e to the negative x times the derivative of the exponent, which is negative 1. So I'm subtracting again, right back where I started actually, but that happens with ease. So now I need to recognize that I'm going to be setting the second derivative equal to 0 and finding out also where the second derivative does not exist, because both of those, as long as they're points in the domain of the original equation, are possible inflection points. So if you have a negative exponent, you have a denominator, and you need to put it in the denominator. And the way we're going to do this is we're going to factor. And I'm going to factor e to the negative x out. I already have a 1/2 out, so now I'm taking more out. So this will be 1/2 e to the negative x coming out. And if I don't know what I get inside from factoring, I just rewrite what I had before. And I divide by whatever I'm factoring out. And that's going to then be, for the second derivative, is equal to 1/2 e to the negative x times, and here I'm subtracting the exponents. So you're doing x upper exponent minus lower exponent, and we all know what x plus x is. If you're walking down the street and you had to do x plus x, you would say it's 2x. So our new exponent is 2x, e to the 2x. And for the second term, they're the same, so they cancel, and that's just 1. I'll rewrite the second derivative now. So f double prime of x is equal to e to the 2x minus 1 over 2e to the x. So the 2 is certainly a denominator. This is moving to the denominator. This binomial is staying in the numerator. And we are going to set equal to 0 to find out where the second derivative is 0, possible inflection points, and set equal to 0 to find out where the second derivative doesn't exist, possible inflection points. So we'll start off with, let's do 2e to the x equals 0. And you can divide, so this is a denominator, you can divide by 2, and you get e to the x equals 0. And there's no value that will make e to the x be 0. If we put 0 in, e to the 0 is 1. So this has no solution. And that means there's no possible inflection points from there. And then our other one, we have e to the 2x minus 1 equals 0, and this one will pan out for us. We'll add 1 to both sides. E to the 2x equals 1. And then I'm going to apply the natural log to both sides to free that x from the e. So natural log e to the 2x, maybe I can, equals natural log 1. Got away without having to rewrite it. And so this is 2x equals natural log of 1, but the natural log of 1 is 0, which you can put into your calculator if you ever forget that. So I'll divide by 2, but I get x equals 0 over 2, which is 0. And that is a possible inflection point. I will not know if it's an actual inflection point until I test the concavity. It has to change on either side of it. So let me move up. Let me keep my second derivative in sight there, because now we're going to do our number line. We have a possible inflection point at 0. So we're going 0 to infinity and on the right, and negative infinity to 0 on the left. And we can test negative 1 and 1. Choose easy values, you might as well. We're testing those in the second derivative, and I'm moving up again. Let me just see if I can make this work. There we go. Right there is pretty good. So the second derivative evaluated at negative 1 is equal to e to the 2 times negative 1 minus 1 over 2e to the negative 1. I care if it's positive or negative. So let's move this to the denominator this way, because I can't just flip it into the denominator because I don't have factors in the numerator, so I can just make it its own little fraction. So 1 over e squared minus 1 over 2 over e. Keep in mind that e is approximately 2.71. It's an irrational number. So let's just very roughly, because we only care about positive or negativeness, say about 3. So if I have 1 over 3 squared, about 1/9, minus 1, then my numerator is going to be negative. And if I have 2 over 3, my denominator is going to be positive. So for this interval, the second derivative is negative. And next one, f double prime evaluated at 1 is equal to e to the 2 times 1 minus 1 over 2e to the 1. And again, we care about positive or negative. So in the numerator, 3 squared is 9 minus 1, so we're positive for sure. And the denominator, 2 times 3, positive. So that means that the second derivative evaluated at 1 is positive. Therefore, we have concave down for the left interval, concave up for the right interval, and because the concavity changes on either side of 0, then we have an inflection point. So we have an IP at x equals 0, concave up from 0 to infinity, and concave down from negative infinity to 0. Nope, you want to see, I bet, too. So there you go. There's that one, and hopefully that'll help you with the homework. The homework's really tricky in this section. They really are make you do a lot of algebra to simplify this stuff. Let me know if you have questions.